global environment. Then screen then. So just 2 minutes, I will explain about our corporation profile. Actually, our NLC India Limited is a Navaratna CPSC incorporated in the year 1956 under the administrative control of Ministry of Coal. Our main business is mining, power generation, and trading the power. So NLC has set its footprint in pan-India mode in the states of Tamil Nadu, Rajasthan, Uttar Pradesh, Odisha, Jharkhand, and Andaman Nicobar Islands. So NLC operates 3 open-cast lignite mines at Neyveli, 1 open-cast lignite mines at Barsingsar in Rajasthan, and an open-cast coal mine at Talibara in Odisha. So NLC is also operating 4 lignite-based pithead power stations at Neyveli and 1 lignite-based power stations at Barsingsar, Rajasthan. So coal-based power station at NTPL is also operating at Thoothukudi, a joint venture between NLCL and Tamil Nadu Generation and Distribution Company. So NLC is also forayed into a renewable energy sector. Presently, the company is operating solar power plants in various districts of Tamil Nadu, Andaman, and Nicobar Islands. NLC is the first CPSC to cross 1 gigawatt capacity of solar power generation. Now the company has become the member of international solar alliances. NLC is aiming to achieve a total renewable energy capacity of 4,531 megawatt. NLC has joint venture with Uttar Pradesh Rajya Vidyut Utpadan Nigam Limited is setting up a 3 into 660 coal-based thermal power station at Katampur, Uttar Pradesh. So NLC is entering into coal mine projects also and has commenced coal production in Talibara at Odisha. So this is our pan-India presence. So at Neyveli, we are having lignite mines and power stations, and also Rajasthan, we are having mines and thermal power station. At Kadampur, now we are constructing a power plant by using coal. So Talibara, we are having coal mines, and Andaman Nicobar Islands also, we are having our renewable energy solar power plant. So in Tirunelveli district, wind and solar energy is there, and various among Tamil Nadu, we are having more renewable energy with the wind and solar power generations. So this is our core business, mining. Currently, we are having the capacity of 50.6 million tons per annum of mining capacity, out of which 20 million tons is from coal. So other rest of them are from lignite. So power generation also, where thermal power stations, our capacity is 3,440, and renewable sources, it is 1,370 megawatt of solar energy, and wind energy is 51 megawatt. So actually, I belong to Center for Applied Research and Development. Ours is the in-house R&D project. This was established laboratory during 1958. So we are recognized by Department of Science and Technology way back to 1975. And with the United Nations International Development Fund, we have updated our project during 95 and 2000. So we are doing R&D works on lignite diversification, new product and process development, renewable energy, reclamation of mines, waste utilization, system improvement, and clean technologies, etc. Based on R&D works, process have been scaled up to pilot scale and commercialized and also implemented in the field. R&D works on diversification, new product development, renewable energy, reclamation of mines, etc. Also we are doing. So these are all our sections. So we are having R&D section. So we are doing with the Ministry of Coal Fund through CMPDL and Ministry of Mines Fund and our own in-house fund. And also recently we have started Innovation and Incubation Center with the Indian Institute of Science and Anna University, Chennai. We are having different sections. We are also doing, we are a NABL accredited laboratory. So lignite analytical section, environmental, microbiology, material testing, soil testing, metal testing, general analytical, petrography. So different sections are there. So they are analyzing the regular samples, and also we are having pilot plants like humic acid, biofertilizer, activated carbon, etc. So this is the coal resource available, the different source of resources, out of which coking coal is 23% and steaming coal is 11%. Even compared to oil, it is only 6%. So 4 times we are having more coal. So we have to gainfully utilize this coal for other next generations. So this is the world proven resources of coal. So currently around 100 billion tons of low rank plus, out of which 100 low and high rank high ash content coal is around more than 50% in the entire world. So we have to depend on coal for our energy. So this is our state-wise breakup of Indian coal resources. Out of it, Jharkhand, Odisha, Chhattisgarh, and West Bengal are the main sources. So we are having around 352 billion tons of coal in our country. So these are lignite resources available in the country. So our Tamil Nadu, we are having more than, it is nearing 80% of the lignite sources in Tamil Nadu, and Rajasthan around 13.8% of lignite. So this is our property of, as you are aware, our lignite is containing more moisture, that is more than 50%, 50 to 56% moisture is there. So volatile matter is 26%, fixed carbon is 22%, and ash is around 2%. So this is power sector, installed capacity. You see, more than 51% is comes from our thermal power plant only. Put together thermal coal and lignite, around 53% we are depending upon coal and lignite. So this is the coal uses in power generation. So this is the tons of oil equivalent per capita. So India is around zero point 0.3 tons of per capita coal use. And compared to developed countries like Australia, it is more than 2.7%, and United States, Germany are all are above one tons of oil equivalent. So need for reduction. United Nations Environment Program estimated that for the world to prevent global warming from reaching more than 1.5 degrees centigrade, the world would need to cut carbon emissions by roughly 7.6% annually for next decades. To achieve this set goal in the 2015 Paris Climate Agreement, a combination of carbon capture strategies is required in addition to the transition to low carbon energies. Additionally, the global demand for energy has been forecasted to increase by 50% in 2030, with oil and gas the major feedstock for 90% of chemicals, petrochemical products, and energy. Hence, carbon capture is also known as sequestration, is an effective strategy to scavenge carbon dioxide from atmosphere, decarbonize industries, and promote clean fossil energy production. It has become an effective approach to mitigate global warming and or dangerous climate change. Furthermore, it has become sustainable energy technology that could be used for a long-term storage. This each country's CO2 emission. You see, China, they are emitting around 29%, and rest of the world is 95%. USA is 16%, whereas our India, we are emitting only 7% of the CO2. So clean coal technologies. So coal is used extensively as a fuel in most of the world. So burning coal produces around 15 million tons. So clean coal technology, it is a collection of technologies being developed to mitigate the environmental impact of coal energy generation. The technologies may be split into two main classes. One that increases the efficiency of the power generation process. The another one, we are addressing the pollution caused by the generation process. In India, efforts towards clean coal technology development began almost 3 decades ago. The country has not been able to keep up with the current developments due to lack of funds. We have to put more FGDs, that is flue gas desulfurization. It requires more fund and additional burden for thermal power plants and inadequate environmental regulations. So still we don't have any CO2 emission norms and other things we are not stipulating. And also poor enforcement, insufficient R&D capacity and infrastructures, ineffective collaboration effects with the developed countries, and lack of expertise and information. So clean coal technologies, during the mining, we can management and practice, and we can reduce some extraneous materials from the coal preparation. So in coal, we can use washing and beneficiation. So thereby we can reduce ash and the sulfur contents. So conversion technologies, so we can use, currently most of the power plants are subcritical, operated in subcritical level. So we can go for supercritical and pulverized fuel bed combustion and integrated gasification and combined cycle we can go in the conversion technologies. Post combustion cleaning also we can do, and particulate and gaseous pollutants removal also we can do. So burning coal give rise to variety of waste which must be controlled or at least accounted for. So-called clean coal technologies are a variety of evolving responses to late 20th century environmental concern, including global warming. However, many of the elements have been applied for many years, and they are coal cleaning by washing has been standard practice in developed countries for some time. It reduces emissions of ash and SO2. Electrostatic precipitators are used in our thermal power plants. Thereby, we can collected more than 99% of the fly ash. So all the fly ash are used effectively by cement companies and brick making companies. So we are 100% we are utilizing the fly ash, and also bottom else also used for road construction, road laying, and other embankment like that we are using. So currently we are setting flue gas desulfurization units to the existing new thermal power plants. So that construction and other works are going on. Thereby we can reduce the sulfur dioxide emissions. So low NOx burners allow coal-fired stations to reduce nitrogen oxide emissions up to 40%. Coupled with deburning techniques of NOx can be reduced by 70%. Increased efficiency of plant up to 46% thermal efficiency, around 50% expected in future, means that newer plant create less emissions per kilowatt hour than older ones. Advanced technologies such as integrated gasification and combined cycle also it gives more than 50% of the sun. Ultra clean coal reduces ash below 0.25% and sulfur to very low levels, mean that pulverized coal might be used as a fuel for very large marine engines in place of heavy fuel oil. There are at least two UCC technologies under development. Gasification, including underground coal gasification in situ, uses steam. Sequestration refers to disposal of liquid. However, waste products can be used productively. In 1999, European Union used half of its coal fly ash and bottom ash in building materials. So, fluidized bed combustion, here limestone and dolomite are added during the combustion process to mitigate SO2 formation. The flue gas desulfurization, also called scrubbers, and removes large quantity of sulfur and other impurities. Low nitrogen oxide NOx burners, integrated coal gasification is already discussed. So selective catalytic reduction achieves NOx reductions of 80 to 90% or more, and it is deployed on approximately 30% US coal plant. Electrostatic precipitators are always used in our thermal power plants to remove fly ash and other dust particles. Efficiency improvements to raise plant efficiency and reduce carbon dioxide and other emissions. While some efficiency technologies are commercially available, others such as ultra supercritical pulverized oil and require continued research and development demonstration. Improved efficiency at existing plant can reduce CO2 emissions by 10 to 16% by 2025, and new units could reduce CO2 emissions by as much as 30%. Axi-fuel combustion, high-efficiency fuel cells to operate on a range of domestic fuels with virtually emissions-free performance at unsurpassed efficiencies. Advanced high-efficiency combustion for generating systems with increased operating temperatures, new computerized controls, improved burner designs, and higher performance turbines. Hydrogen production, a cleaner energy carrier via gasification. So carbon dioxide capture and storage. So here the post-combustion capture from flue gas using amine solvent and chilled ammonia can be tried. And free combustion capture using IGCC to isolate capture and CO2 before it is released. Axi-fuel combustion using pure oxygen and boiler to significantly reduce the dilution of CO2 in the exhaust gas system. This is the carbon sequestration options. The power produced by power stations, the CO2, it can be used in terrestrial sequestration. That means by growing more trees that can absorb CO2, and we can store it in the ocean, and also enhanced oil recovery. So we can inject that CO2 into the oil wells, depleted oil wells, so that we can improve the recovery of oils also. So flue gas separation and oxy-fuel combustion. So separation of CO2 from flue gas. CO2 can be separated from flue gas mixture through solvent absorption, physical absorption, membrane separation, and cryogenic distillation. So current scenario, presently CO2 is captured from flue gas through liquid absorption with solvents such as Selexol, Rectisol, and monoethanolamine. This process is both. So we are planning to have a this CO2 sequestration at our Barsingsar power plant at one unit with BHCL. They have given some proposal, so we are working on it. So we are going to capture at 125 megawatt plant at Barsingsar, Rajasthan, combined with the hydrogen also from that CO2 and hydrogen. So these are all the physical absorption materials used for CO2 capture: activated carbon, zeolites, microporous, mesoporous silica, carbonates, carbon molecular sieves, and metal organic frameworks. So algae also can be used because they are green and blue-green algae. So they will take for the photosynthesis. They need carbon dioxide. So that will produce more biomass, and from that we can produce bio oil and other things. So this are the CO2. These are the algal captures. So this is the sustainable, safe, and no need to transport CO2. So generate biomass. So we can produce biofuel, chemicals, and fibers. So this microalgal sequestration also. So we have done at our thermal power plant at thermal one expansion with NIT Trichy and also Pondicherry University. So we have trapped the flue gas from a chimney, and we have standardized it, and we have stabilized that one with some treatments, and we have fed that carbon dioxide to the algal photobioreactor. So thereby we can get more biomass, and that we have utilized for producing the biodiesel. So that project we have completed. So this is another one project. We have done upgradation of brown coal within Pope Steel, Japan. So this upgradation of brown coal is nothing but our coal is having more than 50% moisture. So they will the technology, they removes all moisture. It is a 0% moisture is there. So it's calorifically is normally our lignite is having 2200 to 2300, whereas after UBC, that's upgradation of brown coal technology. So we can increase more than 5000 kilocalories. So this can be very well used in the ultra supercritical boilers. So we have with funding from MITI, that is Ministry of Environment, Trade and Economics of Japan, and also Coke Steel. Japan, we have done this project during June 2012 to 2012. So we have provided lignite to their plant at Indonesia. So they have prepared and we have studied the product, but the techno-economically it is not very.
Sir, please conclude, please.
Yes, yes, sir.
Please try to restrict the time limit.
Yes, sir. So this is upgradation of brown coal. Here, lignite is mixed with asphalt and kerosene oil. So, so after this evaporator, this oil is separated, and during the separation, wastewater also come. So we can during the flash drum, we can get dried lignite. So this can be used in the ultra supercritical boilers. So this is the benefits of UBC. Calorific value of UBC product increases. Prevention of spontaneous combustion. So long distance transport is possible. So reduction in auxiliary energy consumption in boilers. Reduction of CO2 emissions. So underground qualification also. At present, India lignite deposits are within 150-meter depth and within ratio of 1 is to 1.5 are being mined. Though the total geological reserves of lignite in the current country is estimated 44,000 million tons, the reserves within 150 meter depth amenable to open cast mining is only 8,800 million tons, which is only 20% of the reserve. The balance 80% of the reserves are available at greater than 150-meter depth. So could not be exploited with the presently available technologies in India. So problem of mining at the slope failure due to unconsolidated nature of overburden in the presence aquifer and presence in the presence of aquifer, large quantity of groundwater pumping, high stripping ratio, environmental problems, huge quantity of overburden handling, mine closure, and post-mine closure management. For development of this deep-seated lignite resource, underground coal gasification is the best option. So here, underground in-situ conversion of unworkable deep-seated and thin stream steep dipping a coal or lignite into the combustible production gas. So underground coal gasification operation is initiated by drilling two adjacent boreholes into the coal seam and injecting pressurized accidents like hot air, oxygen, or steam into the coal stream, igniting the coal seam and recovering the combustion gases through the adjacent borehole. The connectivity between the injection and producer wells are made by special linking techniques. So it is the UGC process. First well drilling, then gasification, gas gathering, and transportation. So two boreholes. This is coal ignited and the combustion maintained by injecting the air or oxygen and steam. Resulting gases brought to the surface by secondary borehole. So uses of product, this UCG gases consist mainly of mixture of hydrogen, carbon monoxide, methane, carbon dioxide, and higher hydrocarbons. A new gas after processing can be utilized for power generation in integrated gas combined power plant of suitable capacity. So advantages of underground coal gasification are less dust, noise, and visual impact, lower water consumption, low risk of water.
Sir, please conclude with the only mentioning the clean coal technology initiatives.
Yeah,
Not
yes.
all the advantages and disadvantages in spite
Okay,
of.
sir. So our work, sir, NLC has proposed UGC project at Raneri Black and Rajasthan, sir.
Okay, sir. Okay, I understand, but please stick to the theme of the Econnect Pro event.
Yes.
And please cut short and conclude, please. Otherwise, we have to be very manage the whole.
Okay, sir. Another 2 minutes, sir. I will conclude. Okay.
Yes.
So this IGC. So this integrated gasification combined cycle. This also the gasification process produces clean coal gas and which fuels the combustion turbine. Coal is combined with oxygen in the gasifier to produce gaseous fuel, mainly hydrogen and carbon monoxide. This can is then cleaned by a gas cleanup process. After cleaning, the coal gas is used in the combustion turbine to produce electricity. So combined cycle means this design consists of combination of turbine and generator to heat recovery steam generator and a steam turbine generator. The exhaust heat from the combustion turbine is recovered in the heat recovery steam generator to produce steam. The steam then passes through the steam turbine to power another generator, which produces more electricity. So this is the integrated combined gasification cycle. These are all the history of IGC power plant. So this is why integrated gasification combined cycle. It needless to explain that gas-based power plant is more efficient than the pulverized coal. Implementation of the project will reduce the use of metallurgy and other industries scarce and expensive coke. Mixing of higher grade coal is technically totally eliminated, so only local coal and high ash coal can be used. Significantly improve the environment by reducing the harmful dust and gas, create high performance. So this are all another one. So gasification technology, currently we are working with the BHCL to produce, and we have visited a Trichy unit and Hyderabad unit. So based on, we have given our sample also. So they have tested and they have given this composition, syngas composition also. So based on this, we have written on MOU with the BHCL to produce, to conduct feasibility study for setting up a pilot plant for lignite synthesis to syngas integrated with clean coal, clean power generation by IGC and other things are. So concluded. So we have also working on our lignite to methanol and also lignite to diesel also for clean coal energy. So that tendering is on the way, sir. So fossil fuel based power plants are the major source of carbon dioxide emission, which leads to global warming. The physical and chemical methods followed to mitigate CO2 emissions are not economically viable. So conversion of captured CO2 into a valuable product is the need of the hour. More research is warranted in this direction to mitigate global warming. So sustainable power development calls for adoption of clean coal technologies to be explored to mitigate global warming. So thank you very much for opportunity given, sir.
Thank you very much, sir, for your elaborate and very good lecture. Now I request all the participants for forwarding us forwarding this some questions to the speaker. You may kindly send some question. Is there any question, please? So I think there is no questions from the participant. We like to switch over to our next lecture. I would request our next speaker, Mr. Amit Kulsrestha, GM Ntpc, to deliver his lecture.
Good morning, sir. Am I audible?
Yeah. Yes.
Thank you, sir, for providing me this opportunity. I am very much thankful to the host and CSIR and all the dignitaries who are present here. Let me share the slides. Is it visible, sir? I hope the slides are visible.
Yes, visible.
Okay. So NTPC in 2017 started an experiment with the biomass co-firing. I think all of you are aware about that. I will just give a brief introduction about that. Because of the high pollution problem and the air pollution problem in the Indo-Gangetic belt during winters, the reasons were identified that the biomass as the agricultural waste used to be fired in the Punjab and Haryana region, and that was creating a lot of trouble. So Ntpc took the initiative and then it started exploring this mixing of agro waste fuels into with coal. So the initiative was led by me, and then I experimented at Ntpc Dadri by mixing various fuel ratios, and then we found that up to 10% we can safely mix the biomass with coal. So the biomass pellets were first made with the agro waste, and then those agro waste pellets were mixed with coal in 10% proportion, and we started firing that. So the major constraint was that the supply chain availability of this kind of fuel was not very much well established, because it was a new initiative and we wanted a lot of material fuel for this, and only the smaller applications were using this kind of fuel. So there was not well established suppliers. So we tried to establish the supply chain by encouraging the vendors, and then gradually in 2-3 years we were able to create interest among more than 100 vendors, and until now we have already fired around 70,000 tons of biomass along with coal in our various 14 power plants. So this biomass, as you know, is a renewable resource, because whatever carbon is absorbed during the growth phase of the biomass, it is when you burn it, that carbon only is released, and because it is a short cycle, say around 3 months or less than 1 year, so it does not result in increase of the net carbon dioxide into the atmosphere, and INFCCC recognizes this as a renewable carbon neutral fuel. So also this contains very negligible amount of sulfur. Most of the biomass have very low sulfur content, and the ash content is also low, say from 2% to maximum up to 10%. So this way this fuel is very clean, carbon neutral, and we can classify this as a clean coal, clean fuel. So we have gone further into advancing this technology, and we are trying to now explore the torrefaction process to torrefy or convert this biomass into charcoal, and that enables us to mix it in greater proportions, or maybe even 100% of the fuel can be replaced if some pre-processing of the biomass can be done. So what are the advantages compared to other renewables like solar, wind, and biomass power generation? Has several other advantages, like improving the air quality by discouraging open burning of biomass for elimination, utilization of already existing thermal power infrastructure with minor changes. As you know that this creation of solar or wind capacity requires establishment of new plants, but here only the change of fuel is done, and whole your so-called dirty power resources are converted into clean fuel power plants. So elimination of waste while producing power is another advantage. While you are producing power, you are also clearing the waste. So discouraging primitive use of cooking, thus improving the health of the users. So when this biomass is used in the like this firewood is used for cooking purpose, or this biomass is used for some this application of like heating, etc. So that create a lot of smoke, and by providing this alternate market, we are able to discourage this primitive use, and the smoke which is causing the health hazard is eliminated. So this can also increase the availability of biomass for other this organized energy recovery and creation of rural jobs and increasing farmers' income. So these are certain advantages of this. So now, what are the challenges? The challenges are that higher cost than conventional power, because this fuel is generally more costly at this moment than coal. But as we all know that if we want to implement the clean coal technologies like this carbon capture, or what my previous speaker has elaborated, the various methods, that will also increase the cost of coal-based power if that becomes essential, mandatory to eliminate the greenhouse gases. Then in that case, we can safely say that this will be a cheaper option, and make the biomass power will be a cheaper option. It may contain higher chlorine and alkali metals, which may pose challenges to the boiler operation and metallurgy. So this requires some pre-treatment of biomass. If we are able to reduce these alkali metals of chlorine, or maybe eliminate them, then it becomes easier to fire into the boiler. And flame temperature reduction, if volatile contents are high, is another challenge, because the reduction in flame temperature reduces radiative heat transfers, and then the steaming rate may be affected. Maybe you may require some derating of the boilers. However, if you are able to reduce the volatile content by torrefaction process or by some other process, in that case, this effect can be neutralized. So then the another challenge is the supply chain constraint, as it is a new area and there are no organized setups for collection and conversion of this material into fuel. So collection challenges due to low density and horizontal spread of the biomass. While you are mining coal, you are going down, and the same machineries you can use for increasing the yield of the from the coal mine. But here in this case, you need to provide the machineries in a bigger geographical area to collect a lot of biomass based fuel material, and then convert it into either charcoal or maybe pellets. Availability of the commercial technology is another problem, where the conversion of this biomass into charcoal is not yet commercially developed at large scale. Ntpc is trying at some locations. I will brief you about that. So these are some of the issues. So now I think I have missed one slide. This potential, yeah. So the how much energy we can generate using this kind of fuel. So what is the potential? Agro waste is around 350 million ton per annum, which is wasted. Although we produce a lot of agro waste, but it is used also as a fodder and in other applications also, for industrial applications also. But this much 350 million tons per annum is wasted. So it has no use. It either it decays and increases the methane in which is a very high global warming potential gas, or it remains unutilized, or people burn it to get rid of it. So that create pollution. So this 350 million ton is that quantity. Municipal solid waste is another kind of biomass, which is around 62 million tons per annum. Estimate is that it is around this much. And then surplus forest litter is around 104 million ton per annum. So if we have a conservative estimate, the total is 516 million ton per annum. And biocharcoal production reduces it by around 60%. So around 300 million ton per annum you can make a very high grade coal. And this is the calorific value is around 4,000 to 5,000. Then this can also be so this biocharcoal then can easily be used for fuel for the power plants. The grindability is good. The chlorine and other material, these alkali materials are also reduced to some extent, not to very high extent, but yes, some reduction is there during torrefaction process. Ash content is slightly increased, but is even after torrefaction, it is not as high as the thermal grade coals. So at the most we can get 20%, 15 to 20% of the ash content. So for the very poor quality of biomass which has higher ash contents. So the total billion units which are produced by thermal sector is around 1260 billion units according to the Ministry of Power website. And the total this is around using this you can produce around 540 billion units. This 300 million ton of biocharcoal you can produce around 545 billion units, so which is 40% of total fossil-based power generation. So the 40% of greenhouse gases can straight away be reduced using this technology. So if we go with this kind of torrefaction process, so this is this was about the potential which I wanted to discuss in the beginning, but somehow I skipped that slide. So also, what is the Ntpc experience? I have already shared this. We were the pioneer of biomass co-firing, where under my leadership we did the test firing at Ntpc Dadri, and then we started the procurement process for rest of our plants and fired about 70,000 tons of biomass. Then we are right now installing a torrefaction plant at Varanasi. So Varanasi plant is a big commercial scale plant where 600 tons per day of biomass, mostly these municipal solid waste biomass, will be torrefied. So, which is the most difficult kind of biomass which for torrefaction. The agro waste and the forest waste are easier to torrefy. So we are experimenting with this municipal solid waste in Ntpc in Varanasi plant. For that, we have installed a pilot plant at Ntpc Dadri a few years back. After the successful operation of that, now we are installing a big commercial scale plant at Varanasi. First unit is expected within few days, maybe by 15th of August this year, and planning to install few pelletization plants also, where the torrefaction process will not be used, only the simple pelletization of the agro waste will be done in Punjab. So few plants there also we are in the process to install. Let us see when they see the light of the day. So also we are doing some research, and I'm engaged in some research work at an MIT University. We are focusing on energy recovery from biomass there and exploring the Himalayan forest residues biomass, which is creating forest fires and damaging precious forest wealth. So you hear such incidences before this monsoon season during the summers that there are a lot of forest fires. So they called us, and the Uttarakhand government and the forest officers they wanted our support in this. So we started some projects with MIT University doing research on how we can utilize those biomasses without harming the environment. And whether they will create any issues in the forest ecosystem or not. So all those things we are exploring. So major concerns regarding forest fires are pine needles, lantana, and Mexican devil. So characterization of these biomass and their torrefaction and use their use for power generation are being examined at MIT University. We are exploring possibilities to convert biomass into other high value products also there. And this is these are some of the pictures. You can see this pine needles, raw pine needles. They have GCV, high GCV value of around 4,700. Carbon content is around 49%. Ash content is 2%. And then we are able to torrefy these into high calorific material of 5,500 around kilocalories. Carbon content is also increased. Ash content remains low. And the initial deformation temperature, which is due to the alkali is lower temperature, we are able to see that it increases. So torrefaction process increases the IDT also, and even this is higher than what is the IDT of conventional coal which we burn in our power plants. So typical coal values, you can compare that this fuel is even better than in terms of GCV and carbon content and ash content, it is far better than the thermal grade coal. So maybe we are doing some further research on characterizations and various the presence of various other elements in this, and hopefully we will be able to use this material also for power generation. So this is the scanning electron microscope data. You can see this pine needle, Mexican devil, and lantana waste charcoal. So this can also be converted into activated charcoal, or maybe the coking coal also we can make using these materials if the degree of torrefaction is high. So in conclusion, we can say that biocharcoal is a promising clean coal technology and have potential to fully or partially replace mineral coal in most applications. In addition to be a renewable fuel, it has several other advantages like low waste generation, lower emissions, improvement of air quality, and creating more rural wealth. Ntpc has shown the way, and now it is the time to scale up the biocharcoal utilization. I would request SIMFER and other CSIR institutes to work to research in this direction so that biocharcoal utilization is possible at commercial scale. MIT University Noida is also conducting world-class research in this area. Even the institutes can collaborate with themselves in this research, and biocharcoal and aims to contribute to scaling up of the biocharcoal utilization for energy recovery. Thank you. So this is all my presentation. If you have any questions, we can.
Thank you, Mr. Kulchester, for your nice presentation, and you have elaborated the potential of this bio coal in power plants, and it can reduce 40% of the GHG emissions in the power plants. So my initiative, I think, has been taken under the National Mission for Utilization of Biomass, and most of the power plants has started the utilization of the biomass for as a clean coal technology initiative. So successful, I thank Ntpc for its successful implementation, and I think all other power plants have also started in this direction. If the participants have any questions, they can forward it to Dr. Kulchester.
Thank you, sir.
Yeah, good morning, sir. This is Vishwanathan from Rensol Power. We are very impressed with the presentation on your validity of the biomass and torrefication methodologies and conversion to pellets for utilization. There is a particular type of biomass called energy cane, which is supposed to be ideal with maximum yield also in cultivation. Can you tell us whether that is any aspects of interest to cultivate the right kind of biomass for continuous production, sir?
Energy cane.
Yeah.
I am not aware of that. Can you elaborate something?
No. I also heard this from another forum in which an eminent speaker had mentioned this. It is supposed to be a type of cane which is developed by the agricultural universities in Tamil Nadu, which actually are specifically tuned for maximum cultivation output in a given acreage.
Okay, I understood your point. There are some vegetations which are grown just for the purpose of energy recovery, because their growth is very high, and you can grow them in a smaller area only for the production of energy. So those alternates are good, but what is the drawback is that they will take some of your resources to generate that kind of material, and we already have lot of waste material in our country, which is creating lot of problems because we are not able to dispose of safely in an environment friendly way, like the agro waste, like the municipal solid waste. like the forest residue, which is creating so much of problem, forest fires. So first aim should be for the biomass to energy recovery should be using these kind of resources which are already waste, which are not being utilized presently. And once we exhaust those resources, I think those initiatives which the universities have taken to develop the energy crops can be further explored to increase the proportion of biomass utilization in our country. So I think those things are a little bit futuristic. Right now, we should focus on the waste materials which are creating environmental hazards.
Thank you, sir. Point well taken, sir. Thank you, sir.
Thank you very much. I think I should move to the next lecture. Now I would request Dr. Buddhadev Bagchi, ex-advisor L&T Power, to deliver his lecture.
Am I audible?
Audible, sir.
Yes.
Okay. Nice. Let me share my presentation first. Is it okay?
Visible.
Okay. Very good. Now we were going to my presentations. I am really thankful to CIMFR authorities, and also especially Dr. Mrs. VA SLV, the principal scientist, and also Dr. Mukherjee for inviting me and giving this opportunity to speak something about clean core technology. Now, my first speaker almost covered I will say the 60% of my subject, the CO2 capture technology. So I will add something above the topics. Now that is the picture you know about the global climate change and net zero emissions. The COP, that is the Conference of Parties 15, Paris Conference. The main our agreement was the limiting that increase the temperature of global by 2 degrees centigrade, or our effort will be 1.5 degrees centigrade. That we know everybody. And to achieve this target, our first action will be reduction of greenhouse gas emissions. And to reduce this greenhouse gas emission, the next target should be the reduction of fossil fuel, including coal, in industrial applications. And next, the green energy solution, renewable energy, hydrogen generation, hydrogen applications. That is the next target. And we know in Glasgow, UK, the last COP26, there all countries taken oath to target the net zero emission by 2050, but India taking oath by 2070. Net zero emission by 2070, but rest of the countries, they have taken the oath by 2050. So that is the overall scenario of ambition climate change, global climate change, that we know everybody. The first one, the COP15 and the COP26, if we follow this, definitely the coal use will be reduced gradually. But we know very well, especially for countries like USA, China, India, Australia, this country, their consumption of coal is very high level. I am showing this picture. And Australia, China, Japan, USA, India is a high amount of coal consumption per capita. And these countries, GDP, national economics, that depends on the coal production and coal consumption. So this country cannot avoid the coal production or coal consumption. So rapidly reduction of the power generation from the coal is very, very tough. And that will affect the GDP and national economy of these countries. So considering this actual scenario, you see, I am showing you that according to International Energy Agency coal report, the coal consumption, on just a minute. Coal consumption will increase at an average annual rate of 3.9 to 1.18 tons in 2024 on the back of GDP growth of 7.4 between 2020 to 2024, which will partially be fueled by coal. The picture by IEA, so that we cannot avoid. Secondly, you see, the India, China, USA, the driving of the global coal consumption to record level as early as next year. And that will be another, I will say, negative part not tally with the COP26. And if we follow this actual scenario of the coal use, definitely it will aggravate the local and regional and global pollution problem. So definitely here, considering the COP15 Paris Agreement and zero pathway announced in recent COP26 climate summit and values of coal consumption for national economics, that is the GDP growth, India needs more efficient clean coal technology. That this is a value and importance, significant importance of the clean coal technology, especially for India, I will say. So definitely the attempt by CIMFR, the one clean coal technology, really it is very appreciated. And the industries throughout India, they should also follow these clean coal technologies to follow the COP15 and COP26. But the clean coal technology, there are different methodology, starting from mining, pre-combustion stage, that we know already. My previous first speaker has already explained that from mining, the washing, verifications we can do. Next, the supercritical technology, that is, ultra supercritical, advanced ultra supercritical technology. That also can reduce the emissions. Then fluid-based combustion system also there. Oxy-fuel combustion also there. And also, the after post combustion SCR, FGD system also there for NOx and SOx capture. But here only one thing: the technology which are available and which are working successfully are not capable to capture CO2. And CO2 is the, I will say, the one of the greatest enemy for environmental pollution. And 80% global warming is due to CO2 emissions. So until and unless we cannot capture CO2 or remove CO2 from flue gas or emissions, we will not achieve the COP15, the ambitious climate change, or COP26, the zero emission by 2070 or 2050, whatever maybe. Very difficult. So considering this, and what is the impact of CO2 emission, you see, that already told. Now the CO2 emissions per kilowatt hour electricity generation is 915 gram, or about 1 kg, you can say, roughly. It is 750 to 915, maximum 1 kg, you can say. And this is a graph. As per the present scenario, that if we follow without any clean coal technology or CO2 capture, this will be a scenario up to 2040, the rapidly growth of CO2 emission in the environment. And as per the global forecast will be 43.08 billion metric ton in 2050 if we don't control the CO2 emissions. So in this respect, the only solution is the CO2 capture, utilization and storage technology, CCUS, the only solution. It is an emerging trend and innovation of clean coal technology. Now, CO2 capture, utilization and storage technology already is running in different countries. Somewhere commercially, somewhere it is a pilot projects. Okay. Most common separation capture technology usually done by following methods. The chemical absorption, that already told, physical absorption, membrane separation, cryogenic distillation, and also the by microalgae biofixation. There's a common 5 CO2 capture technology that world or globally at present it has been used. Now, apart from this, there are various R&D work on CO2 capture technology. The advanced R&D work, monoethanol amine, MEA, an alternative observant to conventional amine. Conventional amine we generally use alkanol amine, but here we are using monoethanol amine to increase the CO2 absorption capacity. Then by another also combination of the DMCA and DPA. It also increases the absorption capacity of the CO2. Next, by hydrate method, trusted hydrate method, formation of and dissociation of cathode hydrate method. The latest research work. Another also research work has also done by aqueous solution of potassium carbonate as an absorbent. Next, R&D work also done on calcium looping process using calcium oxide as a solvent for capturing CO2 from flue gas. And another also that has been implemented as a pilot project, the Alstom-Chill ammonia process. In ammonia process, ammonia will be changed into ammonia carbonate or ammonia bicarbonate. And here the energy consumption, energy required for this process will be lesser, and absorption capacity will be very high. About 90% CO2 absorption capacity will be high. And another also research was the aqueous solution of potassium hydroxide. So these are the R&D already have done on CO2 capture technology. The present scenario you see on CO2 capture technology in the world, commercially CO2 capture projects as a part of ongoing commercial operation, and pilot CO2 capture projects for testing, developing, and demonstrating CCS technologies. Now, commercially, CCS or CCUS are being used in Australia, USA, Canada, Ireland, Norway, UK, and other countries. Canada has 3 large-scale projects in commercial operation in Canada. The USA at present now 38 commercial facilities in operation, and others at the development stage and R&D stage. In Europe, 13 commercial facilities in operation or various stages of development. 1 in Ireland, 1 in Netherlands, and 4 in Norway, and 7 in United Kingdom, UK. These are running, commercially running. Asia Pacific, Australia, China, Japan, Indonesia, and other countries are supporting CCS projects and have significantly developed their policy, including financial development for CCS. So they are also going to implement. Australia, they have already started. Commercial, they have also started. And some pilot projects they have also started, Asia Pacific countries, including our Middle East also. India, about India, I will come later on. But the available CCUS are not efficiently useful for industrial requirement because of the following reasons. You see, definitely commercial running, pilot projects also running, but they have some drawback or disadvantages. Technically not viable, lower CO2 capture efficiency, large energy consumption, corrosion in absorption process. The first technical disadvantage. Highly expensive. For example, it leads to 35% increment in generation or production cost for 90% CO2 capturing. So can you imagine how much it will affect the commercial area? It is not viable at all. Second part, the third most part is the CO2 capture. After capture, it is stored, transported and stored in a geological store or ocean. It needs huge pipeline, and storage is not so easiest task. It is highly commercially costly. Technically, it is not so viable. And third is the leakage part. There may be chance of leakage from the storage CO2 storage. That may create the environmental pollution further, a danger for the environmental pollution. And one is the microalgae cultivation. Is also definitely it is a very efficient way of CO2 capture, but this is the most highly expensive, especially for microalgae cultivation process. But capturing is very efficient capture. So these are the disadvantage of commercial available or pilot CO2 capture technology projects. Now, business future and also ongoing R&D work is going on some areas to make the technology more efficient, commercially viable, economically viable. So these are the name of the projects just undergoing. Nanoporous material called metal organic framework, MFO. It is a spongious. It is a sporous and a high internal surface are there. The capacity, CO2 capture capacity is very high level. The Cornell University, they have invented one material, nano sponges. Very micro sponges materials are there. that could also improve the carbon capture economics. The third material is the combination, you can say MFF and a part of polymer. It is about 90% CO2 capture from the power plant flue gas. And another is the copper silicate crystal. As per the Korean University, Sogan University name, it is SGU. That can also capture the CO2 much more efficiently. Now research is going on still now. Further, the CO2, the flue gas can be injected into the underground rock, and the CO2 will be, when the rock it will form the carbonate form. So that is a turning carbon into rock to remove CO2 emissions. Third is the CO2 conversion turning to methanol at low temperature.
Sir, if you kindly try to conclude because of shortage of time.
Okay. Turning carbon into nanofibers. So these are the research are going on. Now, IEA scenario analysis has constantly highlighted that CCS will be important in limiting future temperature increases to 2 degrees Celsius, and we anticipate that this role of CCUS will become increasingly significant if we are to remove oil below 2 degrees Celsius. So this is the role of CCUS in future, and accordingly, global carbon capture utilization storage market is expected to grow from $1.62 billion in 2021 to $1.91 billion in 2022 at a compound annual growth rate of 17.6% the future. So accordingly, India has taken the plan. The Department of Science and Technology has established a national program on CO2 storage research in August 2020, and they have made a call, the CCS Research Development Pilot Demonstration Project, known as ACT, or Accelerating CCUS Technology, which was scheduled to start in September 2021, but date has been deferred. It will be February or March 2023. The India government's plan and attempt to implement CCUS in India. And definitely, this is the target as per the COP 15 and COP 26, Glasgow, UK. So this CCUS or CO2 capture technology will be the most emerging trend or innovation of clean core technology for India. So we should take the advantage of ACT to implement CCUS technology in our countries to achieve the target of zero net pathways or zero net emissions by 2070. So considering this India government plan, I propose CIMFR, CSIR, as they have already done some R&D work on CO2 capture technology, and CIMFR has potential capacity, opportunity, and high expertise in clean core technology. I propose to meet the industry's requirement as per COP 15 and COP 26 and achieve the government of India target. It is proposed the CIMFR CSI can independently deliver their expertise for further R&D work on CO2 capture technology and deliver a pilot project which will be highly efficient and commercially viable. So this is from my side presentation. Thank you all. Thank you very much.
Thank you, sir, for your nice presentation and covering all the most of the aspects and exciting features of the clean coal technologies, its challenges and everything you have covered. And thank you for your expectation from CSR, CIMFR. And I request all the participants to forward questions to Dr. Bagji, if very few short questions. I would request Dr. Bagji to take very few short questions from the participants.
Okay, sure. I think no question is there.
I think no questions. Any questions from the participants? He has, Dr. Bagji has covered all the most of the interesting aspects and very bottlenecks and challenges for the present clean coal technologies. So we should have some questions from the participants. Okay, if any questions, we can take help of expert like Professor Bagji, Dr. Bagji, and I would request participants to forward any questions to him personally through
Sure.
number. Thank you very much, sir.
Thank you.
Now I request our next speaker, Dr. Chanchal Samanta, Chief Manager, BPCL Corporate R&D Center, to deliver his lecture. One question is there.
Prakash Nondiram.
Hello.
To NLC.
Professor Bagji, Dr. Bagji.
Dr. Bagji nahi, NLC.
NLC.
Aap Samuratam.
Okay.
This is the question.
Hello, sir.
Professor Sundaram.
Yes, sir.
Professor Sundaram,
Yes,
you
sir.
have a question from Prakash Chavan Dandiram. Please, it has been highlighted in the question side. The question is whether gasification of lignite is proposed as well.
Yes, sir.
Will be with steam or only air or oxygen?
Sir, that is not decided, sir. But currently we have written MOU with them. So further things are in discussion, sir. With combined with IGCC and production of products like hydrogen, ammonia, urea, and ammonium nitrate like this, sir. So first non-binding MOU signed. Now we are in the discussion, sir, with the BHEL.
Okay, thank you very much.
Okay, sir.
Yes, any other question?
No question. Now next.
Now I request our next speaker, Dr. Chanchal Samanto, Chief Manager, BPCL Corporate R&D Center, to deliver his lecture. Dr. Chanchal Samanto, please. Dr. Samanto, is there any connection problem? Dr. Samanto is on.
Hello, am I audible?
Audible, sir.
Yes.
Sorry for this. I was unable to unmute.
Okay.
Let me share my presentation. Is it
Visible, sir.
is it visible? Visible?
Yes. Yes.
Thank you very much, and sorry for the disturbance. Respected Dr. Basu and Director CSR Shimphar, Dr. Mukherjee, Chief Scientist and Event Coordinator CSR Shimphar, my fellow esteemed speakers and scientists. First of all, I would like to thank organizer for having me here. I strongly feel academic industry interaction, collaboration, need of the hour in the emerging changing scenario. We cannot solve emerging problems with yesterday's old style of working in isolation and slow speed of execution. We need disruptive approaches, speed and agility to solve today's and tomorrow's problem. And thus, I feel collaboration is key. Before going into detailed presentation, let me allow to speak about our company, who we are, and what we do. BPCL is the second largest state-owned companies. We are the third largest refiner in India, having 14% Indian refining capacity. It's also seventh largest company by turnover. We own 3 refineries, more than 19,000 retail outlets, 54 LPG bottling plants. We operate across length and breadth of the country, and we deliver LPG even in the remote part of the country, and we are really proud for that. Energizing lives is our motto, and we promise to deliver pure for sure in every our activities. And BPCL R&D Center is located in Greater Noida, near Delhi. It is in Uttar Pradesh. And it was established in 2001. We have a vibrant team of scientists and engineers from reputed national and international institute. And we also do a lot of collaboration with various national and international institutes to accelerate our R&D program. You can see we have published more than 200 research articles, more than 130 plus patent files already filed in India and abroad, and these numbers are increasing. BPCL R&D is a DSOR recognized lab, and we are looking for developing technology for cost-effective solution for this company. You can understand we operate very large-scale refineries, and operating refinery profitably need a lot of process optimization, energy saving studies, selection of right catalysts, feedstock, and so on. Since our company is a net emitter of carbon, and we have internally set the target to become carbon neutral by 2040. So now we are seriously engaged in finding technological solutions so that we can offset CO2 reduction and reduce our dependency on fossil fuels. So thus we have started our R&D activities in various renewable alternative energy and biofuel areas, as well as synthetic fuels from CO2 and syngas. So we are all talking about sustainable development, and it is the only forward because we have emitted enough CO2. And the global CO2 concentration has reached an unprecedented level above 400 degrees centigrade. So unless we look for circular economy, we will not be able to sustain in the longer term. So since the conference is all about clean coal technology, and BPCL R&D also has done a lot of research on clean coal technology, especially coal gasification and coal syngas valorization to liquid fuels through FT route. We bank on our experience and we have further extended our research activities through both in-house research activities and through collaboration for converting syngas to other valuable chemicals, methanol, dimethyl ether. We need to remember that India still highly dependent on coal. Although government has taken giant step to decarbonize our power sector and set an ambitious goal of 500 gigawatt of renewable electricity by 2030. Our dependency on coal will last for quite some time because we have experienced during this summer that even the redundant coal power plant government is telling that you generate power. Unless the renewable power generation is backed by the power backup facilities, coal is going to last for quite some time. But in order to reduce the carbon footprint from the power generation, what we can do, we can capture CO2 and then converting CO2 through electrolyzers or thermocatalytic route by converting syngas, by converting CO2 to syngas through reverse water gas shift. And when syngas is available, lot of downstream technologies are commercially available. So then we can put CO2 in the circular economy. In case of the coal gasification, one of the most important parameter we need to look that to purify syngas, because syngas conversion processes are highly sensitive to catalyst poison. And that's why it should need to free from all the contaminants like chlorine, hydrogen sulfide, COS, and so on. So if we look into the research trend on CO2 valorization, majority of research focus are in the area of CO2, methanol, and CO. And major global companies in the world are also looking for the 7 different kind of CO2 utilization options, like methanation of CO2 for production of synthetic natural gas, reverse water gas shift reaction for converting CO2 to syngas, dry reforming of methane. This is also one of the important area the world is looking for to tackle both CO2 as well as methane emission. And then after getting syngas, the conversion of methanol, and then methanol to light olefins like hydrocarbons, ethylene, propylene, CO2 to fuels through methanol, this MTG process, methanol to gasoline, and other cyclic carbonates or carbonates. So if you look into the various CO2 valorization option as per International Energy Agency, the fuel is going to have medium-term impact in terms of climate benefit, but it is going to reduce significant amount of CO2 emission further into the atmosphere because fuels are used in a huge quantity. Other as hydrogen technologies are emerging, typical coal gasification produce huge amount of CO2, and that CO2 need to be captured for further utilization. Similarly, the commercially available SMR process also produce significant amount of CO2. So that's why we need to move slowly from black, gray, blue to green hydrogen. And government of India is also putting significant thrust for the producing of green hydrogen. And national green hydrogen purchase obligation is going to be a law after a few years or months. And that's why even these oil companies are also gearing up for setting up green hydrogen production units. And BPCL is also has internal plan to produce significant amount of green hydrogen for refinery uses. So if you look into the methanol scenario, just like crude oil, this is also an important commodity which India is highly dependent on import. And more than 5,000 crores worth of foreign currency we spend for importing methanol. And this number is gradually increasing. Niti Aayog is also pushing this M15 program, just like successful E20 program, that methanol blending in the gasoline. So this number will significantly increase. And unless we produce methanol domestically, we have to import huge amount of methanol from the other countries. So that's why CO2 utilization to methanol is a very important step, I feel. And Indian government is also, Niti Aayog particularly, pushing this project. And Coal India is also taking this project very seriously. So methanol production process has inherent challenges. And this is exothermic reaction, equilibrium limited. So this is purpose conversion for syngas to methanol is limited to 15 to 20%. So that's why we need, and also catalysts operate in a very optimum range of temperature. If there is a high temperature and if there is no, during exothermic reaction, it is not efficient removal of heat, then catalysts lead to irreversible damage. So that's why a methanol reactor need to be operated in a very narrow range of temperature. And also we need to have a particular hydrogen by CO2 ratio. This is called R factor. So in the range of 2 to 2.1. Typical SMR process produce very high amount of hydrogen, while coal gasification typically produce hydrogen by CO ratio in the range of 1.9, 0.7 to 0.9. So coal gasification also need to have coupled with water gas reactor to enrich hydrogen so that we can get the stoichiometric amount of hydrogen by CO ratio of 2. So methanol synthesis directly from CO2 is much more challenging than syngas to methanol. And if we look at the methanol yield with respect to the feedstock CO and CO2, we can clearly found that CO2 based feedstock or CO2 only methanol production has much lower conversion and yield compared to the syngas. So, and also this technology is not available readily. They are the big licensors like Johnson Matthey, Haldor Topshoe, Lurgi, and commercial plants are actually really big in size. So 5,000 to 7,000 tons per day capacity, while Indian producers have the maximum capacity of 500 to 700 tons per day. That's why Indian methanol producers are not competent enough from their global peers. That's why we are importing more than 85 to 90% of methanol. You can see that we have also
Sir, if you kindly try to converge and conclude because of passage of time.
So BPCL R&D is also working on CO2 to methanol through various internal and external collaboration. And FIFI sponsored the CO2 to methanol development project way back in 2014. BPCL along with IIP Dehradun has done a lot of fundamental research in this area. And you can see we have published a number of papers in reputed journals. We also collaborated with MS Breathe, a startup company incubated in JNCSR, Bangalore, and where we are piloting their CO2 to methanol project in the larger scale. BPCL, these are the some of the commercial CO2 to methanol plants. China has taken significant step, and they are making constructing one of the largest so far CO2 to methanol plant, having the capacity of more than 1 lakh tons methanol per year. Similarly, like methanol, LPG is also being imported in India. It's more than 50,000 crores India spent for importing LPG. And if we can convert CO2 to methanol and then methanol to DME, or CO2 to syngas and then converting CO2 to DME, then it will benefit India immensely. So you can understand that syngas to DME process has inherently much more benefit in terms of thermodynamic than converting syngas to methanol, then methanol to DME. We have also carried out in-house R&D program through research fellowship provided by FIFI for direct for development of catalyst and process for direct conversion of syngas to DME, and also we filed some of our promising catalyst recipes, and also we publish our findings in international journals. All this catalytic process has inherently challenges in terms of catalyst scale-up, and BPCL has experienced and also developed know-how how to commercialize lab recipes to pilot scale formulations through third-party collaborations with Chemi and other Indian catalyst manufacturer. And some of our catalyst recipes we have developed and commercialized are in use in the refineries, some such as the gasoline reductions catalyst, and also catalyst used for the hydro finishing and hydro and also LOBS catalyst, live oil based stock. So these are some of the challenges we need to give shape to the catalyst. And in summary, BPCL R&D has experienced and also develops significant know-how in the coal gasification and also converting syngas to chemicals and fuels. We have also pursuing development of energy efficient process for the CO2 capture and further utilization of CO2 to methanol, DME, formic acid, and other valuable chemicals. We also have developed know-how for commercialization of catalysts from lab scale through pilot scale through third-party collaboration. And BPCL R&D Center is also open for collaborating with national and international institute in this CCU area. And finally, I would like to thank BPCL management, Dr. Chiranjeevi Thota, for extending the opportunity to present here, and FIFI for providing Patriotic Society Fellowship for conducting fundamental research in this area, and my BPCL collaborators, students, and BPCL friends. Thank you very much.
Thank you very much, sir, for your thought-provoking lecture and your presentation, and projecting the real scenario and your experience in this clean regarding the initiatives for clean coal technologies. And I would request participants to forward questions, if any. participants. So I request our next speaker, Mr. M. Viswanathan, Managing Director, Rensal Power Private Limited, Chennai.
Good morning, everybody. Am I audible?
Audible, sir. Audible.
Sir, yes, sir, audible.
Yeah. So good morning to Dr. Basu, Director, CSIR Simfer, and Dr. Mukherjee and Dr. Ashish for giving us the opportunity to be present in this eminent forum of panelists on the topic of clean coal technologies. At the outset, we would like to, give our background as a renewable energy company. We are into design and engineering and implementation of large-scale power projects in renewable energy, especially solar power. And being a person in commercial scale power generation, I would like to underline the fact that coal is not going anywhere. It is not possible to do away with coal in the near future. But what is possible is probably to reduce the dependence on coal for energy security. And in this direction, we have been working for the last several years and carrying out many efforts to work on solutions which can go hand in hand to increase the canvas of renewable energy into storable as well as usable forms, you can say. I would like to make a presentation of the slides to illustrate our background in this subject, sir. Can I share the slides? Yeah. So we are actually into large-scale power generation using solar power, and we are also experienced in designing and implementing large-scale projects for rooftop solar in megawatt scale. What you are seeing here is the rooftop solar which we have installed for a commercial center for a shopping mall, which is about 1 megawatt capacity. And this is the mall which utilizes this power. We have also built many ground-mounted solar power plants which are producing grid-scale power for export to the grid. And this is one of the projects of our construction in Andhra Pradesh. And this is the control room in which all the power electronic controls like inverters and other systems and SCADA are all housed. We are also capable of designing and building HT yards in high voltage level in order to be able to export the power to the grid. We are giving you all this background to make the fact to be understood that we are already exposed to commercial scale power and its issues. That is what we are trying to tell you here. And we are now moving on to the next stage of our continuity in this subject. Now, we have been looking at hydrogen as a viable alternative to kind of conversion of green energy. So as you can see, hydrogen as a feedstock has got huge potential. It is practically able to become a central stage of the energy domain. It is possible to use it into refining, fertilizer, steel, chemicals, and blending with natural gas, transportation, and energy storage. And as our earlier speaker, Dr. Chanchal had mentioned, hydrogen is going to be converted to DME, dimethyl ether, which is almost an equivalent substitute as a drop-in substitute for diesel, which is already being pursued very vigorously in Europe. And also it has got the parameters of LPG so that it can be transported more safely. Again, hydrogen can also be made to produce green hydrogen, green ammonia, which is going to be another form of energy carriage for hydrogen. So hydrogen has emerged now as the new hope, and it has got multi-industrial usage in establishing energy security. That is the point we wanted to put across here. As we all know, not all hydrogen are created equal. The hydrogen which comes from coal is probably the most polluting form, and this is called brown hydrogen. And of course, the color codes are almost now familiar to all the scientific community, because almost it's a topic of a daily interest in all forums, both in the business domains as well as in the scientific domains. So Rensol has now set its goals on developing green hydrogen production technology, embracing the concept of Atmanirbhar Bharat, and we are basically a company which innovates in technology areas. So we have moved into the development of green hydrogen prototypes. Now, as you know, the basics of hydrogen production is electricity and water, which is of course the simplest process, which is electrolysis. And we are relevant here because we already are working with electricity from solar energy on a day-to-day basis in our business in a large scale. And therefore, the other components are also available to us. I will explain how it is happening. See, we have now developed a solar operated 1000 LPD RO plant. This is a modular unit which has been designed for easy installation in any site. And this unit is capable of converting your groundwater to analytical grade water, which can be used for as a feedstock for hydrogen production. So this stage we have first crossed, because we wanted to ensure the sustainability of doing a project on a commercial scale, because we are basically commercial scale project people, and therefore we address all the issues connected with the availability of components as well as scalability when we consider even to do R&D. So this product is readily available with us right now. And as a progress in our green hydrogen journey, we have made progressive steps in pursuit of green hydrogen development. We have harnessed renewable solar electricity. As you have already seen, we are capable of designing megawatt scale power plants to generate the high power DC and currents which are required in electrolysis process. And we have already developed the solar powered RO plant for water feedstock for the H2 generation. And already now we have also developed indigenous Indian electrolyzer prototype unit, which is in a mature state of development for establishing distributed H2 generation, because as we have seen, on-site H2 generation is probably the need of the hour in the, at least in a initial stage, wherein we are able to establish the fact that green hydrogen is a reality, and then we can move on to large scale centralized generation, where we can think of conversion into ammonia or DME or methanol or similar byproducts. So thus we are in the pursuit of green hydrogen goals for energy security for the future. Now, as we know, one important factor of renewable energy is it is actually fully dependent on coal, for your information, because all the power plants which we design and install in megawatt scale right now, these are all what is called as a grid dependent plants. Like, our inverters are used in order to synchronize the power generated from solar to be connected with the grid after sensing the availability of power in the grid. Now, what is this availability of power in the grid? This power is the thermal energy or coal-based generation, which already comes in the grid. And only after sensing that power availability, our inverter is able to latch on and then pump the green energy into the grid. Therefore, it is very clearly understood we are riding piggyback on thermal energy resource, namely coal. That's why I told in the initial point of my talk itself that doing away with coal is only an idea, not really a possibility in the near future. But going for green hydrogen helps in two ways. It gives energy security, which is also storable in terms of so many available chemically convertible technologies. And huge decarbonization is, apart from the electricity, which is only 18% of our total energy canvas, balance 82% also needs deep decarbonization, wherein hydrogen, especially green hydrogen, can play a very vital role. Therefore, we see green hydrogen generation and having a control over the technology, especially with Indian resources, is very, very huge step in moving forward in the concept of decarbonization, which is essentially clean coal technology. So that is how we feel we are connected in this topic. So we feel there is a huge opportunity, especially with giants like BPCL working in the picture. I think some kind of collaboration with people who are in need of the solutions will also help in moving forward in a faster track. On the side of technology collaboration, we have invested in technical capabilities to design and develop indigenous solar-powered water treatment plant and a robust and solar-compatible electrolyzers for making green H2. Rensol is into technology collaboration with already with institutions like IIT Madras and ARCI. We are working with them on hydrogen, solar-based solutions for hydrogen. And also we have an MOU with Fraunhofer of Germany in solar thermal storage. Rensol is also now currently working with one of the senior scientists at SIMFER for development of gas separator membranes. And that is the channel through which we got as an industrial associate of SIMFER, and we are in this forum today. We thank you for the opportunities. And we now look forward to work in partnership with the end users of hydrogen for carrying out some field trials in the areas of on-site green H2 generation in the near future. And that trials would establish the possibility of going to scale later on. So we are basically people who are very experienced in solar on-grid and off-grid topologies to suit client applications and power backup. We provide turnkey solutions in solar energy for concept, design, engineering, procurement, erection and commissioning, operation and maintenance. So our contact details are also there in this page. And we thank you for patient listening and a wonderful opportunity to be part of this eminent forum, sir.
Thank you very much for your wonderful lecture and projections of your contributions in this particular field. I would request participants to ask any questions. So I think there is no question right now from the participants. And now I would request our last speaker, Dr. U. Chandrasekhar, to deliver his lecture.
Good morning, sir. Chandrasekhar here. Can I share my presentation?
Yeah. Yes, sir.
Is the presentation visible, sir?
Yes, sir. Yes, sir.
Okay. Once again, good morning to all the dignitaries, and thank you very much for this opportunity to share a few functional insights connected with additive manufacturing and the kind of influence that this technology has been having on various sectors, including energy sector. It's a possibility that many of you have heard about the term additive manufacturing, or more ubiquitously used term 3D printing. Fundamentally, what do you infer by the phrase additive manufacturing is we are looking at the possibility of transforming the digital designs into physical parts in single step. In a conventional manufacturing, you go through many steps, including development of the tooling, geometry specific, fixturing, machining, and finally, you end up with a part of our choice. In additive manufacturing, in a toolless manner, whatever may be the complexity of the part, we can translate the digital design or a CAD model into a physical replica in one single step, which is going to have significant impact on the time of preparation as well as the ease of manufacturing. Having said this, the additive manufacturing technology comes into forefront in various formats. The most commonly seen additive manufacturing machine is called FDM printer, which is seen on many tables, wherein filaments are extruded at high temperature so that they turn into viscous state and finally liquefied and deposited on a build platform. And in this particular technology, you can make the parts out of thermoplastics like ABS, PLA, polyethermide, polyether, ether ketone, etc. The other technologies, which are equally well known in the world of additive manufacturing, are stereolithography, through which you can make photopolymer resin parts, laser powder bed fusion, through which you can make metallic parts, and direct energy deposition, wherein you can selectively deposit a wide repertoire of metallic materials on the points of interest. With this kind of availability of technologies and materials, if you just take a quick glance at how this particular technology has been put to use in aeronautical sector, to start with, it was just used as a prototyping tool for making the components of a gas turbine engine. Then came a phase wherein using airworthy plastics, the whole interiors of the aircrafts were getting manufactured using additive manufacturing. In the year 2022, as we are speaking, we are talking about making the whole systems, such as ornithopters, quadcopters, being made through additive manufacturing and directly put into the field use. And I would like to spend some time on delineating the influence of this particular technology on the energy sector. The conflict between growing energy demands of the nations put together and the problem of global warming is a grand challenge. And to tackle this challenge, we require many scientific and technological innovations. Additive manufacturing as an innovation in the manufacturing practices has created a niche for itself in terms of producing extremely complex parts directly from the CAD designs out of materials like plastics, metallic materials, ceramics, waxes, and composites, with a significant positive imprint on reduction of the energy requirements. As a schematic representation, I have taken few examples from the sectors corresponding to nuclear, battery management, oil and gas, and fuel cells. If you see on the top left, you can see how the additive manufacturing technology of stereolithography has been made to make nuclear fuels out of thorium dioxide. Just below that, you can make out a metallic filter, which is meant for collection of nuclear debris. And as you can easily visualize, in this case, the precision of features is extremely important, as well as the compatibility with the nuclear radiation. Down below is a very interesting part, C, binder jetting, wherein you can make interdigitated micro batteries with submicron accuracy using the principle of binder jetting, that is, put the droplets on demand. On the top right, you can see the application of the fused deposition modeling for manufacturing of membranes in a microbial fuel cell, and E and F correspond to laser powder bed fusion based additive manufacturing of the parts like pumps, valves, impellers for oil and gas sector. And the introduction of additive manufacturing in this context has led to reconfiguration of the supply chain. That is, whenever a part becomes malfunctional, from a digital repository of the designs, you download the design, you make the part at the point of requirement and test it and induct into the service. So the industrialization of additive manufacturing is an important thing as far as the energy sector is concerned. GE has been doing pioneering work in this particular field for past about 15 years. You can see here a part called fuel nozzle, consisting of nearly 20 pieces that have been transformed into a single part with a phenomenal positive impact on the time compression as well as the cost reduction. So a part with 20 plus, a component with 20 plus parts has been converted into a monolithic design. And till now, GE has produced more than 150,000 nozzles of this kind for their contemporary LEAP engines. So this is one of the places where the industrialization of additive manufacturing is very dominant feature. Here is one more instance wherein Siemens has converted a component with 13 parts, close to 19 weldments into a single part. It's called the burner, used in the energy plant, and the burner, which is made from high temperature resistant cobalt chromium alloy using the laser powder bed fusion, has been put to rigorous testing to ensure its integrity under the thermomechanical conditions that simulate the conditions in the energy plant. So the technology of additive manufacturing has been around for nearly 20 years. So in the initial phases, when the material choices were limited, when the technologies were still evolving, there was an innovation trigger. This happened in the late 90s, and there was peaking of expectations. Immediately after that, there was a trough of disillusionment because of the fact that the materials were not capable of withstanding the engineering conditions that are pertaining to the operable conditions. And in course of time, there were tremendous contributions from multiple disciplines, and by virtue of which there is a slope of enlightenment leading to the service induction of the additive manufacturing. If you look at the current status of additive manufacturing, it's become an interdisciplinary world. It's a confluence of material science, laser physics, design, polymer engineering, metallic materials, composites, tooling, inspection, and process simulation. And if you look at the applications, on the left side, you can see a small part, which is more like a symbolic representation of the final design. Okay, you can call it as an accurate prototype. Two, on the right side, you can see a large module of a gas turbine engine, which has been made with a complex, intricate detailing using the technology of additive manufacturing. So applications are continuously progressing from those of prototyping to end use. And in the recent times, we have seen SpaceX from US and Agnikul from IIT Madras that have proclaimed the possibility of producing a monolithic rocket engine running into almost 1 meter length, and for space applications through additive manufacturing. So the sectors that have been able to derive advantages from this technology are multifarious: aerospace, automotive, defense, healthcare, electronics, etc. But for today's discussion, I limit the applications to those of the energy sector. You can see, I would like to take your attention to the impellers, which are shown on the right bottom. In many occasions in the oil and gas sectors, the impellers could become malfunctional because of the wear and tear which is associated with their service life, or maybe because of the hostile conditions under which they operate. In these cases, it is possible to bring or refurbish the part back to its original geometry and extend its life. It is called refurbishment. So here I am citing the example of MTU engines from Germany, wherein you can see that making of the part is only one part of the challenge, but getting the necessary certification to ensure the endurance, to ensure its strength and integrity under the operational conditions is an activity which consumes substantial time. So whenever we are talking about additive manufacturing, our vision might be connected with the large engineering companies, but in a pleasant manner, hundreds of startup companies have also come to the forefront in terms of integrating this technology into the product development. Even in our own country, there are more than 10 plus startups which are using this technology with a lot of success for energy sector. Just to quote one example, I'm talking about the global example. The Graphene Lab, located in US, is a company which has been able to produce the FDM filaments with the thermoplastic matrix with graphene added in certain composition, and these filaments consisting of graphene and thermoplastic are used for making the disc batteries in lithium poly battery situations. In our own country, there is a company called AMS India, located in Bangalore, which has developed a system that can handle ceramic materials, metallic materials, composites with the multiple heads mounted on a robotic arm to produce the parts with the variable levels of hardness as well as the necessary chemical resistance and mechanical integrity for applications in wide-ranging contexts, straddling the missiles at one end of the spectrum to high temperature gas turbine engine modules at the other end of the spectrum. So the fundamental process in this case is called laser powder bed fusion, wherein high energy laser, typically a fiber laser, a continuous laser, is scanned on the surface of the powder, and because of the interaction between the laser beam and the powder, the particles get instantaneously melted and solidified as the beam is passing through. And eventually you raise the platform down by an extent equivalent to 1 layer thickness, and the process is repeated ad nauseum till the overall height is achieved, leading to manufacturing of a turbine blade, which is shown on the right bottom. So this is a very complex phenomena. You have all the three modes of heat transfer, including the radiation because of the inert gases that are available in the process platform, the convection within the melt pool, which happens because of the gradients in the surface tension leading to Marangoni effect, and the conduction of the heat from the melt pool to the substrate. And the end effect of this kind of a complex scenario, wherein the heat transfer can happen at 10 to the power of 5 Kelvin per second, could be found at the macro scale in terms of distortions and residual stresses. It could also have immediate impact on the microstructure of the part. And last but not the least, there are the phenomena which are at the mesoscale in terms of the surface finish and inclusions because of the process. So to make the parts with the necessary strength and to put them into service, there are a lot of optimization procedures which are put into play. One of the primary examples is considering the volumetric energy density, wherein you derive the density as a function of the laser speed, laser power, hatch spacing, and layer thickness. Try to find out which is that process space, process window, wherein you are likely to encounter keyholing, or if you put less energy, most of the particles remain unfused. So you need to find out the optimal mix of these parameters leading to volumetric energy that is just sufficient enough to melt the part and create a track with the necessary geometrical integrity. So fundamentally, whenever you are looking at usage of additive manufacturing in harsh environment related applications, we are talking about a dedicated effort that connects the process parameters to the microstructure to the property. Just for an example, I have shown in this case how SS316, when it is melted in the powder form using the lasers, provides us with the ultimate strength equivalent to almost like 1032 megapascal, which compares very well vis-a-vis the wrought alloy. So with the right combination of these operation parameters, it is possible to work on wide array of materials, including nickel alloys like Co2 titanium alloys like Ti64, steels, and aluminum alloys. And in some of the cases, we can also make use of this technology for handling the refractory materials, which are otherwise very difficult to manufacture through conventional practices. The other technology which is equally important in case of additive manufacturing for energy sector is called direct energy deposition. In this case, you have got a energy source, could be a laser beam, could be an electron beam, could be electric arc or plasma, and the material is fused as it is being deposited on a surface. And the primary application which is associated with this particular technology in the energy sector is about depositing the material at the point of requirement and bringing the components back to the original shape, and repairing and refurbishing and life extension of the parts is the most important application of the direct energy deposition in energy sector. At the other end, we have got technologies like stereolithography, which can handle photopolymer materials. Once again, in this case, you move a laser beam on the surface of the photopolymer, and the liquid phase converts into solid phase on the infusion of the energy from the laser beam, and you can make these translucent parts directly from the CAD parts. So they are extremely good vehicles for design visualization. And when you are interested in taking up the stress analysis of these parts, you can make 1:1 replicas of these parts, put them under simulated loading conditions, and study them through reflection polariscopes or conventional transmission polariscopes to get first-hand information on the distribution of the stresses as well as the stress concentration factor, through which you can understand the fatigue failure of the component when the design is not optimally done. Whenever there is an instance where the additive manufacturing is not able to provide the solution in the metal of your choice, you can make the patterns, quasi-hollow patterns, using additive manufacturing, and then go through secondary techniques like investment casting to convert plastic parts into metallic materials. So this is called rapid tooling, and this is something which is generally used in the industry when the material of requirement is not directly provided by additive manufacturing. The most ubiquitous technology of additive manufacturing is called fused deposition modeling. It's also called fused filament fabrication, wherein you are sending the filament, which is typically of 1.75 mm in diameter, through an extrusion head. The extrusion head is maintained at a temperature which is slightly above the melting temperature. The build platform has got the mobility in the Z direction. On the extrusion head can move in the XY direction, and the entire part, like this, what I have shown in the bottom, can be made in just few hours by making use of the fused deposition modeling. How is it relevant to the energy sector? In the recent times, it has been observed that the extrusion heads are mounted to the robotic arms, and through controlled movement of these robotic arms, we are able to make parts from thermoplastic materials, including the continuous carbon fibers. And then we can also have layers of epoxy resin or acrylate resin smeared over the surface. And we are able to produce large sized industry relevant parts, including the storage cylinders, using these robotic assisted fused deposition modeling technologies. So if you want to capture the very important characteristics due to which additive manufacturing has become relevant to energy sector, it's because of the fact that we are able to integrate multiple functionalities into the system through re-engineering of the part. You can do customization of the geometries without any loss of time. And in the bargain, you might be able to even cut down the weight. And last but not the least, certification and qualification bodies have got enough maturity now to indicate whether or not the part which has come through additive manufacturing is capable of replacing the part which is conventionally manufactured. So I would like to conclude my this brief talk by delineating some of the possibilities in the near term. Especially if you are talking about the nuclear energy sector, there is so much of emphasis on development of the new design of new alloys for additive manufacturing with good irradiation tolerance and corrosion resistance. And importantly, there is also a traction between the high entropy alloys and the additive manufacturing, which will go a long way in terms of making the cores for the nuclear sector, for the current generation of the reactors, as well as the futuristic advanced reactors. And if you are talking about microbial fuel cells, there are a lot of applications connected with biomimicking lattice structures, and also the application of the macro size porous structures with high specific area for collecting the microbes. The laser powder bed fusion of the titanium alloys and duplex
Sir,
steel.
please try to converge and conclude, sir.
Yeah, has led to reconfiguring of the supply chain. And I would like to conclude my talk by saying that the ASTM F42 committee has set up a subcommittee in the recent times for looking at the ways and means of testing and certifying these materials for practical applications in the energy sector. Thank you very much for your kind attention. With this, I conclude my presentation.
Thank you very much, sir. If there is any questions from the participants, you can communicate the questions in the channel. So, meanwhile, two questions have been forwarded. One questions have been communicated by Sri Pankaj Kumar Arya. His question is chemical looping combustion and its prospects in India. So I would request speakers to address any of our speakers to address this issue. So I can just to address question of Pankaj Kumar Arya, I would say that chemical looping combustion is not now has been progressed much in India. So, but some work have been done in Simpar, CME, Durgapur, and Niri. But with Indian coal, it can be done. It is a very futuristic technology, and it can be done in done through gasification route only, because Indian coal is very high as coal. So for the gasification route, it can be done, but it's very early stage, too early to comment on this technology to be implemented in India. So it's very it is in very primitive stage. So I think I have given a little bit of projection on this technology. So next question has been forwarded by Dr. Sudeep Maiti. He once a non-renewable source of energy is used, it always emits CO2. We can only recycle CO2. So is not CCS a misnomer? Ultimately, we emit CO2 in multiple cycles. Can the panel of the experts, if a panel of the experts address this question, the audience would be happy.
May I?
Yes. Yes.
You are correct. We need to stop using the fossil resources. So far, whatever we have emitted, we need to trap or capture. Then only we can. There is two technology. One is carbon positive, carbon neutral, or carbon negative. If we take back CO2 from the atmosphere and then put into the recycle, then it is partly carbon negative. And if we are emitting and then it is taking back and putting into the cycle, then it is a carbon neutral. So that's why renewable power is going to be a carbon neutral, since we are not using further coal or natural gas. So there we are not emitting any CO2. But if you are emitting CO2 and continuously through the power generation by using coal or natural gas, then it is going to be a carbon positive. So large scale carbon negative program is need of the hour to increase the CO2 concentration into the atmosphere further. I hope.
Yes, please continue, sir.
So that's why you have seen that as per the International Energy Agency, the impact of recycling fuel through products from CO2 is going to have a medium-term impact on the climate, but the magnitude is very high. It is more than 5 gigatons per CO2 that can be put into the circular loop for the production of fuel if we start using CO2 as a feedstock. Otherwise, traditional fuel production and converting that fuel to energy, this generates a lot of CO2, and that is continuous addition of CO2 into the global atmosphere.
Okay, thank you, sir, for addressing this tricky question. So I would now, I think we are in the verge of the March end of the this program. And Dr. Pinaki Sarkar, thank all eminent speakers for delivering thought-provoking lectures and for sharing futuristic views. And they have also shared their vast experience in this event. And I also thank to Professor Suddhasatta Basu, Director CSR Simpar, and Dr. N. Kalaisilvi, Director General CSR, for their valued guidance to make this event a grand success. I am also thankful to all participants and audience, NFDC team, and technical support team. I am also thankful to Dr. Devendra Singh and CSR team to make this program a grand success. So, thank you all, and I think we'll be interacting based on the outcome of this event. Will be continued to interacting with each other, and for the benefit of India, and to bring out the India's target of net zero emission by the year 2070. Thank you all.
Thank you very much.
Thank you very much. Thank you all.
Thank you, sir. Thank you very much, sir.